So you're going to need a couple things in order to successfully complete your cross-country flight plan. The first thing is you're going to need a sectional. There's a couple different versions or places that you can get one. SkyVector is one option. ForeFlight is another, and that's what I'm going to be showing on this video is ForeFlight. Some students have the Garmin Pilot app that is also an option, or if you're old school, obviously you can go find some paper charts, although that is probably not what you're doing. The second thing you're going to need is your E6B flight calculator. I call it a whiz wheel because it's more fun than E6B flight calculator. But either the one that has the wheel on it or an electric version. Third thing you're going to need is a plotter. There are two different types of plotter. I have one that also has a rotating wheel. Your plotter might not have a rotating wheel, so we'll either make a different video or you'll be able to see how to use different versions of a plotter in another class maybe. You're going to need your POH. You're going to need some weather info. Hopefully you have your POH. That's where we're going to get our performance calculations. For weather, there's a couple different places. You can go to 1-800-WX-BRIEF. That's my favorite is 1-800-WXBRIEF.com. ForeFlight has the same information. Garmin Pilot has the same information. If you want to call 1-800-WX-BRIEF, that's kind of an old school method that is getting outdated, but it still works. You'll also need a flight planning form. Obviously, that's what we're going to turn in to our flight instructor before we go on our cross-country flight. Make sure you use pencil, don't use pen. Pretty straightforward. You're gonna make mistakes, and we don't want them in pen. The next thing here is your flight plan form. Up at the very top, you see a bunch of things, and on the bottom, this is our nav log. This is the meat and potatoes of your flight plan form, and by the time everything is done in this video, you will have filled out this entire thing. Buckle in, it's gonna be a ride. Good news is, you can take it one step at a time. First thing, we're going to pick a destination, and we're going to draw a line between our departure and destination. So here on ForeFlight, I have gone in, and we're flying from Dubuque to Rochester. It's KRST. And on ForeFlight, you just go into the top of your map, you type in KDBQ and KRST, and it just draws this line for you. Pretty straightforward, pretty easy. You can see there it's a total of 120 nautical miles, and we'll make note of that. The next thing is that we have to pick checkpoints along our route. So the very first checkpoint is going to be our departure airport. That is Dubuque. So we will write in there KDBQ, and the first actual checkpoint along the way is going to be our top of climb. So I'm going to write in here KDBQ and then TOC. Now that's going to be based on our ground speed, so we don't know where that is immediately. We'll have to wait until we get weather to know where that is. But every checkpoint that we have along the way should be anywhere from 10 to 25 miles. I like to do 15. So if I measure from Dubuque, I'm going to try to find a checkpoint that is easy to identify that is approximately in that range, right? 10 to 25. So there would be 15 from Dubuque, but there's really nothing there. You can see there's kind of a tower just below me. So what if I call Cassville my checkpoint? I can see that off the right side of my airplane, and it should be pretty easy to identify on a clear VFR day. So I'm going to use that as my first checkpoint after the top of climb. So I'm going to mark my route there, and after that, we're going to write it in. It's C74 is the name of the airport. You can write Cassville if you want. It's the same thing. And we're just going to continue this process. After Cassville, we'll go another 15 or so miles and try to find another checkpoint that I can see on the ground. We want things that are easily identifiable during the day in bright sunlight. So towers are not that easy to see when you're up at altitude. So if I go about 15 miles Well, we can see there's not a whole lot. There's El Cader off the left side, but if I go a little bit further, maybe 19 or 20 miles out, off the right side of the airplane is the Prairie du Chien Airport, which is right on the south side of Prairie du Chien. So that would be pretty easy to see. And so I'm going to mark that one as my next checkpoint. And it's about 18 miles, give or take, maybe 19 miles. And what you'll notice is that when all is said and done, the sum of your legs will be a mile or two difference from your total length, just because of rounding errors. But Prairie du Chien is what I'm going to call my next checkpoint, and we're just going to continue this process. Approximately 15 miles after Prairie du Chien, off the left side of the airplane, you would be able to easily identify Postville. So I'm going to make Postville my next checkpoint. After Postville, it looks like Decorah, either the city or the airport. We should be just about over the top of it, so you can pick whichever one you would like. That's about 15, you can see there, maybe 17 to 14 or so miles. So I'll call the city my next checkpoint, and that's about 16 miles. All right, after Decorah, again, we're looking for approximately 15 miles or so. That's just a number I like to use. Way off the left side, you would be able to see the city of Cresco and or the airport, the church airport, CJJ, it looks like. So if we try to see approximately where that is, it looks like maybe it's 13 miles or so off your left wing, you would be able to see that city. So that's what I'll call my next checkpoint. I have found that when you're using 10 nautical miles, you're increasing your workload, and 15 is kind of the sweet spot. If you go all the way out to 25, you have some downtime in the airplane while you're flying it. And at this point, we're getting close to our destination, so we're going to have to figure out where we want to start our descent. If I pretend like I'm not having any descent, I'll just find my next checkpoint. And off the right side of the airplane, it looks like there's the city of Preston, and that's about 13 miles. So I could use that as my next checkpoint. Now, maybe that's going to be where I start my descent. Maybe I start my descent somewhere past this checkpoint. We don't know just yet. But as I fill in my checkpoints here, we're going to fill in that church checkpoint that I forgot before. We're going to call Preston the next one. Excuse me. And then somewhere, I'm going to have my top of descent. Now, I like to teach a bottom of descent as well. And the bottom of descent is what we're going to get into next. So I know that my bottom of descent, I want to be at pattern altitude as I'm entering the airspace. My top of descent, I don't know where it's going to be. Now, I wrote top of climb here. I meant to say top of descent. That's my fault. I'll fix that in a second. But in regards to where that is, I don't really know. What I do know is that my bottom of descent is going to be at pattern altitude as I'm entering the airspace, and so that's 4 nautical miles away from the airport. So I'm just going to put top of descent in here. Don't know where that is just yet, but I know where my bottom of descent is, and then my last spot is my destination, is Rochester. Now, one thing that I wasn't doing when I was picking my checkpoints was measuring them. You could have been, well, I mean, I was measuring them, but I wasn't writing down those leg distances. So you could have been writing them down as you're measuring them. What I'm going to do now is I'm going to go in and measure all of these so that I can put them onto my flight plan. So this total distance from top of descent, which I don't know where it is, to bottom of descent, is a big question mark. Maybe Preston is the top of descent. We don't know yet. Looks like we have about 13 miles here. If we go the distance from Decorah to Church Airport, 12 and a half, let's just call it 13. The distance here from Postville to Decorah, about 16 miles. Now, you don't have to write your distances on your chart like this. I'm just doing this for the video. You could just write it into your nav log, which I will show on the next page. The distance from our Prairie du Chien checkpoint to Postville is about 15. The distance from our Cassville checkpoint to our Prairie du Chien checkpoint is about 18. And then remember, the one that comes before this is our top of climb. Again, we don't know where that is because it's based on your ground speed. So we'll have to figure that out before we measure that out. Big old question mark. Don't know where my top of climb is right now. But this is all stuff that you can do before the day of your flight. Next thing is that we're going to record our checkpoint distances. So those are just going to go into your nav log now. So you'll notice from Dubuque to top of climb, we don't know. From top of climb to Cassville, we don't know. But I do know that from Cassville to Prairie du Chien was about 18 miles? Yeah, 18 miles. So over in the distance column, where it says leg, that's the top box, it's 18 miles. So this leg is 18 miles. The next leg is 15 miles. And we're just going to record these all the way down. Now you'll notice I'm skipping a box because that box is the distance for what is remaining. This is a box that we're going to fill in at the very end of all of our calculations. So 16 was my next, and we're just going to go through and look at all of our numbers. 13 was after that. Oh, look, another 13. So to get to Preston was 13. Now, from Preston to our top of descent, we still don't know. From top of descent to bottom of descent, we still don't know. But we know that from bottom of descent to Rochester is 4. So we can fill that in. Now, we still have these other 2 boxes to fill in. We'll have to do that once we know what our ground speed is going to be. Next thing, what altitude are we flying at? Well, we have even thousands plus 500 since we're going on a westerly direction. So we have the option of 4,500, 6,500, 8,500, and I'll choose 4,500. So I like to write my altitude as our field elevation climbing up to 4,500, and then we're going to stay at 4,500 all the way throughout our flight until we get to our top of descent. Once we get to that spot, we're going to say top of descent starts at 4,500 and goes down to pattern altitude. So this is where we go 4,500 down to pattern altitude. And we have to figure out what is our pattern altitude. So if we go back to our sectional, we can see that the field elevation at Rochester is 1,317. So I'm looking right here. Let me switch this up real quick. There you go. So 1,317. I round that up to 1,400 and then add another 1,000 on top of that. So our pattern altitude we're going to estimate to be 2,400 feet. And that's where we want to be at the bottom of our descent. And then from there, we're going to go down to the field elevation, 1,317. This is where you're in the pattern. You know, you're doing your 85, 75, 65 airspeeds and setting up for landing. The next thing is winds. We're going to put our winds in. So this is where we have to go get our weather. We need to know the weather at Dubuque during our climb, once we're up at altitude, when we are descending, and our weather at our destination. So I pulled up some weather here. You see a METAR for Dubuque, our winds aloft for the route for Dubuque and La Crosse, and then our TAF. So at Dubuque, winds are 030 at 8 with a temperature of 5. So in the wind column, I'm going to put the direction is 030. The temperature was 5. I forgot the velocity. I had to go back and look at it. And if we double check real quick, yep, sure enough, 030 at 8. Now we have the ability to calculate ground speed for our climb. So once we get to our top of climb, we're going to use our winds aloft. And we're at 4,500, which is right in between 3,000 and 6,000. It's exactly halfway. So we're going to assume that the valid time here of 1,400 Zulu to 2,100 Zulu is a valid winds aloft. And I'm just going to interpolate here between 3,000 and 6,000. The direction is from 050 at 3, and then 010. The halfway point of that is 030. I know this is going a little fast, but we're going to have a separate interpolation video if you're still rusty on that. The winds, interpolating exactly halfway, are 12 knots. And so I can say that at Dubuque, the winds at 4,500 are 030 at 12. If I do the same thing for my La Crosse winds aloft and interpolate between 0.7 and 0.3, well, it's exactly halfway of 0.5 is the direction. If I go to my velocity, halfway between 9 and 16 is 12.5. I'm just going to call it 12. And so the winds aloft at La Crosse are 0.50 at 12 knots. So I'm going to use the 0.30 at 12 knots all the way up until I get about halfway between the Dubuque winds and the La Crosse winds. And that halfway point was right about Postville. So once I get to Postville, now I'm going to switch, and I'm going to use 0.50 at 12 knots. If you look at the La Crosse reporting station and the Dubuque reporting station, about halfway between those, you'll see Postville. And so I'll use these winds aloft until I start my descent. Now I haven't done anything with temperatures yet, but we'll get to that in a second. We want to finish out our winds first, and if I look at the winds at La Crosse at 3,000 feet, they show 0.70 at 9 knots. Now while I'm descending from 4,500 down to pattern altitude of, I think we said it was 2,400, these are probably the winds that I'm going to be encountering. So for my top of descent to bottom of descent, I'm just going to use the La Crosse winds, and then I'm going to use the forecasted winds at Rochester from bottom of descent to my Rochester destination. So 0.70 at 9, and then 0.80 at 7. is what we're going to use for those winds. Now that we have our winds in there, we're going to input our true airspeed. Now this is the part where we need our POH. So true airspeed, there's an entire column for it. Hopefully you remember that on climb out, our airspeed at sea level should be 74, but once we get to 1,000, our climb speed goes to 73. So I always put 73 right here. That's the true airspeed that we're going to have during our climb. Once we get to top of climb, this is where we need to go figure out what our true airspeed is going to be. So you see here in the cruise performance, this is where you should go. You have 4,000, you have 6,000, 8,000, 10,000, 12,000. Well, we're right in between 4,000 and 6,000. So we would have to interpolate these numbers. There's 3 different columns as well. You have your 20 degrees below standard temperature, you have standard temperature, and you have 20 degrees above standard temperature. So the question becomes, what numbers do I use? And the answer is that it's entirely up to you. You get to pick what RPM setting you want to use. So let's talk about these temperatures real quick. We know that we have standard temperatures of 15 degrees Celsius at sea level, and that standard temperature drops by 2 degrees for every 1,000 feet. So if I have my 1,000 feet increments on the left, then the temperature is as shows here. All the way up at 6,000 feet, our standard temperature would be 3 degrees. So these are just standard temperatures that we would expect on a standard day. Now our actual temperatures at Dubuque, if we go back and look at that weather, they show us that the temperature at Dubuque, remember that's 5 degrees. So at 1,000 feet, give or take 77 feet, we have an actual temperature of 5 degrees. Now if we have a standard lapse rate, we would expect 2,000 feet to be 3 degrees, 1,000 feet above that is 1, and so on and so forth. So these are our actual temperatures that we would expect on the day that we pulled this weather. Now if we look at that forecast, the winds aloft forecast for Dubuque, they showed that at 6,000 feet, we had a temperature of -3. You can see that right here. So that -3 is the forecast temperature. So for Dubuque, at 6,000 feet, the forecast says that it should be -3. Well, my actual temperature at 6,000 feet, we're expecting it to be -5. So these are pretty darn close. And the fact that they're so close means that my forecast is probably pretty reliable. So this is a good thing. That tells me that my actual temperatures are probably pretty accurate. Now we have to interpolate to 4,500 feet. The standard temperature would be 6 degrees, and my actual temperature, which is pretty reliable, is -2. So that's a difference of 8 degrees below standard. It's not quite 20 degrees below standard. So technically what we should do then is interpolate between the 20 degrees below standard column on our cruise performance and the standard column on our cruise performance. Now again, this video isn't all about going into interpolation. If you're struggling with that information and how to interpolate, then go check out a different video or ask your professor about it. But what we need to be doing for this example is interpolating to 8 degrees below standard. Remember, you get to choose your own RPM setting. So that's one of the nice things. You know, a lot of students will ask, well, how do I know which number to pick? And the answer is you can pick whatever you want. You want to go at 2,600 RPM, 2,500, that's entirely up to you. But just keep in mind that you also need to interpolate between the 4,000 number and the 6,000 number that you get, so that you're interpolating to 4,500. That's a lot of math to do, and we're going to kind of skip over a bunch of that for this video. But what we're going to just assume is that when we look at this cruise performance table, that we are interpolating. So the assumption is that we are choosing an RPM setting of 2,500, just because that's what looked good to us. We're going to assume that we interpolated to 8 degrees below standard. Again, I'm not showing that here, but I'm just saying, let's pretend like we went off screen real quick and we did it, and when we come back to here. That we also interpolated to 4,500 pressure altitude, and that what we find in those charts is that we have 70% power, that we have a true airspeed of 115 knots, and that our fuel burn we interpolated to be 9.7 gallons per hour. And I like that. What I usually do is about 10 gallons per hour for cruise flight, so this is pretty darn close. Also, you should note that there is a note in the bottom of your cruise performance that says you have to reduce your speeds by 2 knots because we don't have speed fairings. So that 115 that we interpolated is actually 113 true airspeed. Now, we did all of that work just so that we could figure out what is our true airspeed during cruise. So we know that it's going to be 113. That means that we can put the true airspeed in all the way down. Now keep in mind, this is not ground speed. This number is not going to be affected by winds. So we'll keep 113 knots all the way until we start our descent. And then once we get to our descent, our airspeed could change. So we're going to leave this box right here is going to stay blank. I'm going to have to figure that number out. But from my bottom of descent to Rochester, I'm going to call that 75 knots true airspeed, just because that's an average of your downwind base and final of 85, 75, 65. Next, the fun part, we have to determine true course, and this is where we use the plotter. So what you'll do is you'll take your plotter and you'll see that we have our quadrants, right? Our lines of longitude and our lines of latitude. And we've talked about these in class, hopefully. The lines that go up, down are lines of longitude, and the ones that go sideways are latitude lines. So I'm going to take my plotter and I'm going to place the arrows directly on the course with the center lined up on that course line. And I'm going to take the center of my plotter and put it on a line of latitude. So you can see right about there, just underneath on the sectional, is a line of latitude going from left to right. Now, if you don't have a plotter that twists like mine does here, then you will just read whatever it shows. But on mine, you have to line up the lines of longitude so that they are parallel to the lines that you see on the plotter right here. So if I do that, it looks like our true course up in the top left there is showing a true course of about 320 degrees. So that information goes into our true course box. It's going to be 320 degrees all the way down. This is a short flight, and off screen I measured our true course up at Rochester. It was also 320 degrees. Now if you're going long distances, your true course might change along your route, so be careful. Don't just assume that it's going to be the same all the way down. It just happens to be like that in this example. So we have true course there. We need to figure out our wind correction angle, and this is going to be based on your winds. So our winds during climb, we said were 030 at 8, and we're going to go to the wind side of our whiz wheel. So I have that here, and you'll just follow the directions at the top of your whiz wheel, you're going to set your true index to what the winds are at. They are showing 030 at 8. So I put 030 underneath our true index up top, and then I put the center of my whiz wheel and measure, or the center goes onto a nice even number, and I just measure up 8 knots from there. After that, excuse me, we're going to set our true course under our true index, and so we put 320 up top, and then I slide the red dot to whatever my true airspeed is. So 73, there's 75, 74, 73, and you can see the ground speed is underneath the center, that's 70 knots, and I have 3 degrees correction to the right. Excuse me, that's 6 degrees correction. And I know that it's 6 degrees correction because those were in increments of 2. So underneath our ground speed, we're going to put 70 knots, and then here I accidentally wrote 3, but this number should be plus 6. Keep that in mind. I made a mistake in the video, but I'm admitting to it right now. So when we add these numbers here, we come up with a true heading of 326. So now we go back and we do the same thing all over again. We're going to calculate our winds during climb, and we set our winds, we set our winds were 030 at 12 knots. So again, we set our 030 underneath our true index, and we measure 12 knots up from there. So there's 11 and there's 12. We then put our true course, which is still 320, underneath our true index, and we'll slide our true airspeed. The red dot goes to our true airspeed. So we said our true airspeed was 113. There's 100. Go up to 110. There's 111. There's 112, and there's 113. So that shows a ground speed of 108, 109, something like that, and a correction of about 6 degrees to the right. So when I go back to my nav log, we're going to record our ground speed of 108, and we're going to say our wind correction is plus 6. And so we'll get 326 for our true heading. When we'll just fill this all the way down, because these are the same winds all the way until we get to Postville. Now once we get to Postville, our winds change. They go from 030 at 12 to 050 at 12. So now we have to go back to our wind calculator and do it all over again. We're going to put 050 underneath our true index and measure up 12 knots. So I'm going to center up my ground speed on the 110 and measure up 12 knots from there. So right about there's 12 knots. And then I put my true course under my true index. Hopefully you've had lots of practice with this. If not, we'll have another video that you can watch. So now I'm going to put my 113 true airspeed, red dot, and look at my ground speed under the center. It shows a ground speed of about 112 maybe, with wind correction still 6 degrees to the right. So my ground speed goes up. That's nice. And we'll mark this all the way down until we start our descent. And we'll put our wind correction of plus 6. Now, the thing that we said for our true airspeed during descent, we said it would be based on our ground speed. We want that to be exactly the same as what we had during cruise. So if I put my winds of 070 at 9 for my descent, again, center up the middle point and mark 9 knots up from there. Something right about like that. And then again, we put our true course under our true index. Now this is where it gets a little different. I'm not going to move my red dot. I'm going to move the center to be 112. I want my ground speed to be 112, which means that my true airspeed has to be 109. So we're reading it backwards from what we did on all these other ones. Wind correction shows about 4.5, maybe call it 5 degrees to the right. So my ground speed is going to be 109 with a wind correction of 5 degrees to the right if I make my ground speed 112, which I'm going to do. Call it a cruise descent. And then the last thing is that we go and we figure out what our winds are on the ground at Rochester. There's 080, and we said that they were 080 at, 7? And then again, we move our true course to underneath the true index and go to a red dot goes on our true airspeed of 75. Again, that's just an average. And so you'll see that your ground speed is going to be about 78. Our wind correction shows 2 lines to the right, and I made the same mistake I did on my climb, as I called that 2 degrees on the video, but really it should be a +4 right here. So again, be careful, don't make the same mistake that I did. Then we'll go in, we'll take our true course, adjust for wind correction to come up with our true heading. So these numbers just go into true heading. Next, once we're done with this, we'll figure out our variation correction, which will come from the chart. This number here I wrote 322, it should be 324. Now, variation are these magenta lines. Hopefully you remember that. And so close to Dubuque here, when we take off, we're going to have a 1 degree west variation. And as we get closer to Rochester, it's going to change. That variation line that's really close to Rochester is actually a 0 degree variation. So our job is to figure out where does it switch. So if we look about the halfway point, I'm splitting the screen here between these lines of variation. And it looks like either Church or Decorah is the halfway point. To be honest, it's not a huge deal. As long as you pick one of those two, I don't think your flight instructor will have any issues with it. But I think I'm going to say that Church is where we're going to switch that variation. So a west variation is going to be a +1, and we'll take that +1 variation all the way until we get to Church. So after the Decorah, now I switch to +0. And this change will give us our magnetic heading. So again, we just do these numbers here. Magnetic heading is whatever they swap out to be. And we're just going to fill these in all the way down. This is probably one of the easier parts of filling out a nav log in flight planning. And once you have that, you'll need to know your deviation. Now remember, it's specific to each aircraft, so you'll have to actually go out to the airplane and look at the compass card to figure out what your deviation is for your particular aircraft. Now, for this video, I'm just going to assume that I already know those numbers and that it tells me that if I am trying to fly a heading of 330, which is close to what we see here, that I'm going to have a specific deviation or adjustment for it. Let's just pretend like it says on the compass card that you should be subtracting 1. So because my course isn't really changing, it's going to be the same all the way down because it's the same airplane. And doing this will result in your compass heading. So if you had to use only your compass to fly, these are the directions that you should use to fly your airplane using just the compass. right, so we are making progress here. The next thing that we're going to do is fill out our estimated time en route. We're going to figure out what distances we have for climb and descent. So we go to our time, fuel, and distance to climb, and we see that if we are going from sea level, that this chart shows us how much time, how much fuel, and how far we're going to go if we have no winds. Well, we do have winds, so we're going to interpolate to 4,500. Halfway between 4,000 and 5,000 is a time, and our fuel is, again, halfway between there, 1.7. So we got our time is 7 minutes, our fuel used is 1.7. And I'm not even going to use this distance column because that's based on zero wind. We're starting at 1,000 feet. So we're going to subtract out the 1,000-foot altitude because we're already there. So when we take 7 minutes minus 1 minute, we get 6 minutes, and 1.7 gallons burned minus the 0.4 means you're going to use 1.3 gallons in your climb. Now, a little note down at the bottom there says you got to add 1.4 for start, taxi, and takeoff, which means from the time I start to the time I reach my top of climb, I'm going to use 2.7 gallons. That has to go on the nav log as well. So from Dubuque to my top of climb, my estimated time en route is 6 minutes, and my fuel burn is going to be 2.7 gallons. What I don't know is the distance for that leg up to my top of climb. So if I use my E6B, I can put my index pointer on my ground speed, and then I will read the time en route of 6 minutes on the inside ring, and I'll get my distance on the outside ring. So right now I'm putting the index pointer on 70, that's my ground speed. If I go 6 minutes, that's the same thing as the 60. So the outside, I'm already pointed at 70. That must mean I'm going to go 7 miles. So I'll write 7 miles for this distance. And now I can go to my sectional and mark that distance so that I can now figure out the distance from the top of climb to my Cassville checkpoint. So if I come back here from Dubuque and measure out 7 miles, we'll be able to say that that's where my top of climb is going to be. So I'll mark that right there. 7 nautical miles, that's where my top of climb should be. Now the distance from my top of climb to Cassville is what I need to measure next. And that distance looks like it's about 14 miles. So now I can go back to my nav log. I know that's 7 miles to top of climb, another 14 miles to get to Cassville. So now that we've filled in that leg distance, we still need to try to figure out the distance from Preston to our top of descent. That's this box right here. And then the distance during our descent from top of descent all the way down to bottom of descent. That's the part that we need to figure out as well. Now, Preston might be the top of descent, but maybe it's not. So let's go back to our map real quick, and we'll take a look at the distances there. And you'll see that from Preston all the way to our bottom of descent is a pretty good chunk of space. So there's two methods for calculating where to begin your top of descent. And I'll show those to you right now. Let me figure out, here's a blank sheet here. Two methods for figuring out when to begin descending. The first method is based on an assumption that we are going to use a specific rate of descent. So when I use this method, I like to use 500 feet per minute. That's a nice, easy descent. It's easy on your body. It's easy on your passenger's body. But the other method that you could use is that you're going to use a specific distance to descend. So if you already know, hey, I want to get down in 20 miles, this is the method that you would use. But let me go into details on these two different methods. They both basically get you the same thing. The first thing for the rate of descent is that we have to figure out how far down do I need to descend. Well, if we go back to our navlog here, it shows that we're going from 4,500 down to 2,400. So we got to figure out how far is that to descend. Well, if you take 4,500 minus 2,400, you probably already came up with a number. For some reason, my pencil wigged out here. 4,500 minus the 2,400 that we're trying to get down to gives us a distance to descend of 2,100 feet. I think I'm off on a side, just double checking my math, making sure that that works out. Yep, 2,100 feet. Yay, I can do math. Okay, so that's how far down we have to descend. And the next question is, how long will it take us to do that? Well, if we're descending at 500 feet per minute, we're going to take that distance to descend divided by our rate, and that's going to give us about 4.2 minutes. So we know that the amount of time that we're going to be in a descent is 4.2 minutes. Now, we already said that our ground speed was set. So the question is, how far will we travel if we are assuming a specific ground speed? We said our ground speed was 112 knots across the ground. So if I set my index at 112, there's 110, 111, 112, and then I go to a time on the inside ring of 4.2, that gives us about 8 miles on the outside ring. So approximately 8 nautical miles between top of descent and bottom of descent. That's if we're descending at 500 feet per minute. Now, if I measure that out, bottom of descent, come backwards on my route about 8 miles, I'm going to see that my top of descent should be somewhere right about here. 500 feet per minute at a ground speed of 112 shows me starting my descent right there. So I'll just mark that, and that'll be my top of descent at 8 nautical miles. Just a little bit past Fillmore. So if that's the method that you like, I think that's the one that I use most often when teaching and when doing VFR flight plans. Because it's a little bit past Fillmore, you'll have to say, oh, look, there's Fillmore, and then maybe a couple of seconds later start your descent. But if you wanted to say, hey, let's just start our descent at Preston and use a specific distance to descend, then the question becomes, well, how quickly are you going to descend? So if we start descending at Preston, it's going to be about 18 miles. And so that's the assumption, is that we are descending a certain lateral distance across the ground. Well, we still know that we have a specific altitude to lose and that we have a specific ground speed. Well, we said our ground speed was 112 knots, and we said that we are going to lose the same 2,100 feet. So how much time are we going to need is the thing that we're asking ourselves next. Well, if I'm doing 112 knots across the ground, and I'm doing it for 18 nautical miles, I'm going to put 18 on the outside ring and read the time on the inside ring. It's about 9.6 minutes. So 9.6 minutes is the amount of time that I'm going to be in my descent, and I already know that my altitude that I need to lose is 2,100 feet. So I have feet, I have minutes, I need to figure out feet per minute. So if I take 2,100 feet and divide it by 9.6 minutes, that'll give me my descent rate. And so I'm off on the side doing a calculation. Or here, I'll just bring it up. So if we go 2,100 feet No, go away. All right, and then divide that by 9.6 minutes. That's approximately 220 feet per minute. That's a pretty slow descent rate. But it's no big deal if that's what you wanted to do. You could totally do that. So I'm just going to stick with my first method of assuming a 500 foot per minute descent and starting at 8 miles away from my bottom of descent. I like this method better. So I'll stick with this distance. So now I know the distance from Preston to my top of descent is about 10 miles, and to get to bottom of descent is about 8 miles from the top of descent. Now I can go mark those in my nav log. We now know these leg distances. So it's about 10 miles for this one and 8 miles for the descent. Now I can figure out my time en route. I have my distance, I have my speed. Let's go figure out time. Again, this is another whiz wheel thing. I know that I'm going real quick on these, but go check out the other video that we have on using your E6B calculator for more information. What I'm doing here is I'm adding up my total leg distances. Now that I know all of them, remember I mentioned earlier that you should be within 1 or 2 nautical miles of your actual total distance, and that's just because of rounding. I would say if you're off by more than 2 miles, go double check all your measurements because you're probably significantly off on one of them. So when I added all these up, I think I came up with 118, but we know the total distance is 120, so that's pretty darn close. Make a little note there that, hey, I measured 118 when I added them all up, but that's just because of rounding. I know the total distance there is 120. Now again, the whole point of this was to figure out our estimated time en route. So this is also one of the easier parts. I have 108 knots for my ground speed, and I'll use my whiz wheel and I'll put my index pointer on 108. So there's 105. There's 106, 107, right about there's 108. And then I just go measure all my distances, and I look at the distance on the outside ring. So 14 is what I'm going to look for here on the outside ring. And if I look on the inside ring, it shows about 75, 76, 77, something like that. So about 7.7, maybe 7.8 minutes. If you want to round on your times, you should always round up. So I'm going to call it 7.8. And now my speed is still 108. I'm going to look at a different distance on the outside. When I look at 18 miles on the outside, that gave me a time of about 10 minutes. Looking at my next distance on the outside, I read the time on the inside ring. And we're looking at about 8.3. Now, 112 is the ground speed that I have next. So I'm going to slide my index, my 60 rate arrow, has to get, I'm going to slide it to 112. Yep, I forgot to do it, right? So let's go back and slide my index to 112. Hey, look, I caught my mistake. And when I look at my distance of 16 miles on the outside, the inside ring's at about 8.5, 8.6, something like that. So we'll call it 8.6. When we look at our 13 on the outside, it's about 6.9 or maybe even 7 on the inside. And, well, it's the same number, right? 13 for our leg distance gives us a 7-minute time. Looking at the next number, if I'm doing 10 miles, it'll be about 5.4 minutes. Now if I go to 8 on the outside ring, it's about 4.4, something like that. And now I have to change. Let's see, I called it 4.3. Now for this next one, I have to change my ground speed to 78. What I'm going to do is I'm just going to call it 6 minutes right here, because this is really difficult to calculate because you're changing direction while you're in the traffic pattern. What I have found that approach usually takes about 6 minutes. So I'm just going to call it even 6 minutes. And then we're going to go through, we're going to add all these times up to see what our total time en route will be. So off on the side here, I have a calculator on the side, and I'm just ticking off each of these numbers. So I add the 7, I add another 7, I add a 5.4, I add a 4.3, plus that last 6 is going to give me my total time. So I came up with, well, let's see, we've got to get this guy out of the way, I think. 70.4 minutes. It's about an hour and 10 minutes, something like that. And again, on your time, just round it up. You can call it a nice, pretty 71 minutes. The next thing we need to figure out is how much fuel will we burn. It's very similar to your distance, rate, and times. It's technically a 9.7, but I think I end up rounding this to 10 gallons an hour just because it makes calculations much easier. But we're going to do it on the whiz wheel just the same. So if I take my index and I put it on 9.7, right about there is 9.7, again, I'm just going to round it up to 10 and say, hey, we're going to burn 10 gallons an hour. And then we know our amount of time. So 7.8 minutes is on the inside, and I'm going to read the outside now. I see about 1.3 gallons on the outside ring. If I'm going to be moving for 10 minutes, I go to 10 on the inside, and that shows me about 1.7 gallons. If I go to 8.3 minutes, I'm going to come up with about 1.4 gallons. If I have 8.6 on the inside, I'm going to show about 1.4, probably 1.5 is what I'll round it up to. 1.5 gallons. If I'm only going for 7 minutes on the inside ring, it's between 1.1 and 1.2. So we'll call it 1.2, and this number here will be the same. All right, 5.4 on the inside ring rounds up to about 0.9 gallons. And 4.3 rounds up to about 0.8. And then if I go to the 6 minute mark, we'll see that's spot on 1 gallon. Now these are all overestimates. I know I'm not going to actually burn 10 gallons per hour in my descent. I also know that I'm not going to be burning 10 gallons per hour while I'm in the traffic pattern. But I'm overestimating my fuel burn because I'm giving myself a buffer. So the next thing we're going to do is we're going to total up what is all of my fuel burn from the time I from the time I started my engine to the time I land at Rochester. So you can see here again, I'm just putting little dots on the numbers that I'm calculating off to the side on my calculator. And we'll come up with total gallons of fuel that we burn from start to land. If you added up all those numbers with me, you probably came up with something close to 13.7. Let's just round that up even and call it an even 14 gallons that we need for this flight. Not too bad. So that is a good chunk of your flight plan. We still have some other boxes here that we're going to figure out, and we'll get into that next. Our magnetic course, our distance remaining, our ETA, and our fuel remaining boxes are the other things we have to fill in. So we'll start with the distance remaining. That one's easy. You just start with your total distance of 120 and you subtract out each leg. So I started with 7, When I take 120 minus 7, it's 113. Minus 14 off of that goes to 99. Minus 18 off of that goes to 81. Minus 15, minus 16, minus 13. Minus 13 again, right? And we're just going to go all the way down. (14 minus 8) puts us at 6. Now, we see that 2-degree difference, so I'm just going to call the last one 0. Or a 2-mile difference, I'm sorry. We'll do the same thing for the next column. Assuming we're going to start at 53 gallons, we're going to take 53 gallons and minus 2.7. That gives us 50.3. Minus the 1.3 takes us down to 49. Minus the 1.7, and you get the idea. We're just going to go all the way down this until we figure out how much fuel we should have left when we land. This is probably the most exciting part of the video for you. Thanks for being with me. Thanks for watching as we just do simple subtraction. All right, we're almost done with this column here. Once we take off the 0.9, take off the 0.8, and then take off the 1, we should have approximately, 39 or so gallons left. Plenty of extra fuel. No big deal for this short flight to Rochester. Now, we said we had a couple other columns that we were still going to fill out. And we'll go fill out our magnetic course. So remember, your true course and magnetic course, the difference is variation. So we measured our true course as 320. If we adjust for the variation at Dubuque, our magnetic course is 321. I'm just using the columns underneath my variation, or the adjustments underneath my variation column to come up with these. Fortunately, our variation is pretty minimal here, and those are easy to fill in. Talk to your flight instructor or your ground instructor if you have questions about that column. We still have to fill in our ETA column, our estimated time of arrival, and that's based on your estimated time of departure. So these boxes here are based on what time you plan on leaving. You can do math, I'm not going to go through all of them, but we have to know what time we're planning on departing. So up in that time off column, we have our estimated time of departure, and then you're going to have an actual time of departure, right? So what time are you planning on leaving? What time did you actually leave? So if you plan on leaving at 1300 Zulu, then all of these estimated time of arrivals are just going to be, you're just adding the minutes for each leg. So if I leave at 1300, 6 minutes later, it's 1306. 7.8 minutes later, it's 14.8 or 13.8, or round it however you want. 10 minutes after that, 8 minutes after that, so on and so forth. So I'm not going to show you all that here. It's pretty boring. I'm sure you're already excited about all the math we've been doing. And so you'll fill that one in on your own. I'll skip it here on the video. Now, one thing you are going to have to do is once you actually take off, you start a timer, and you're going to be calculating your actual ground speed, your actual time en route, and your actual time of arrival. So this is the part that you have to fill in. The stuff I'm doing in red is what you're going to be doing while you're in the actual airplane. And that's what keeps you busy, making sure that all your calculations are close. So that's your entire navlog. Congratulations. We still have all of this other stuff to do, but that's the part that's going to come up next. for right now, you can be happy with what you've done. Good job. Yay. Take a break. And we'll move on to the next part when you're ready. So we got to figure out your weight and balance. Hopefully you're ready. Well, ready or not, here we go. This is the weight and balance section of the flight plan. And this is just an estimate that you can do the day before. Now, you won't know your actual until you are assigned an airplane the day of or the morning of your flight. So for the estimate, you can just assume a couple numbers. Now, most of our Cessna aircraft are all pretty similar. So let's just say 1,700 pounds is the empty weight. It has an arm of 42 inches, and so when I multiply those two numbers, I come up with a moment for this estimating aircraft of 71,400. Now again, you'll have to change these numbers on the day of your flight. I want to be clear about that. Let's just pretend like you and your flight instructor are sitting in the front, and together you guys weigh 360 pounds. Most of the time we don't have much in the rear seats. I like to put 10 pounds there because my flight bag, my flight instructor's bag, there's some weight there. Baggage area 1, we don't put anything. And then I always put just 10 pounds in the back because we got the chocks and the, maybe you got a quart of oil and the other stuff is back there. For fuel, we're going to assume we have full 53 gallons. That weighs 336 pounds. And then we have to go figure out what is the arm for all of these stations. Now, remember, that's going to be in your POH. And so if we go there, you should be able to see in the weight and balance section what those distances are for the arms. So I'm going to flip through real quick as fast as I can. Flip, 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 flip. And go find this page right here. This is the one I like to use. Because it gives you the numbers nice and pretty. Right? You have your CG arm, and these are all estimates. So we'll use the one for fuel down low in the notes. We'll use the numbers on the far left to figure out what the arm is for the pilot and front passenger. I just use the average of 37 inches. The rear passengers, that's going to be the same no matter what. Baggage area 1 we said was 95. That's not going to move. Baggage area 2 is not going to move. And then we have this zero fuel weight. We also said our fuel was at 48 inches. So I'm going to be multiplying the weight times the arm to come up with my moment. If you are already proficient at weight and balance, you could probably just skip all this stuff. But I wanted to make sure I demonstrated almost everything as far as this sheet, this flight plan goes. One thing that students get confused on sometimes is the zero fuel weight, because what they don't realize is that this box here is also a total column. For some reason we don't have it bolded, but you need to make sure you understand that that is the total of the numbers up above it. So we're just going to add up all of our weights. When we add up these weights, we get 2,080 pounds. We're going to add up our total moment as well. Remember, you never add up the arm. You only add up the moment. If you need to come up with the arm, you take your total moment and divide it by your total weight. That is what's going to get you your CG, or your arm. Now, the total moment on my fuel is the product of the 336 times the 48. So that moment is going to be placed into the fuel moment. When I multiply those two together, I come up with 16,128. And I am going to add the moments and add the weights. So I'm only taking the 86,000 plus the 16,000. And same thing for my weight. I take the 2,000 plus the 300. And then I figure out what the center of gravity is for my ramp weight. I know I'm not overweight, so that's good. But I also want to make sure that my CG is within limits. We know that taxi fuel is going to take about 8 pounds. You can call it 8.4 if you want, but it's that 1.4 gallons when I multiply it by 6. I'm just going to call it an even 8. And I'm going to subtract out that moment. 8 times 48 is 384. And then I realized after that I had forgotten to fill in my ramp weight, the CG of that. So there it is there, 42.55 is also within limits. I know that because it's in the weight and balance section. So now I'm going to subtract out my fuel burn weight for taxi. I'm going to subtract out my fuel burn moment for taxi. And then I'm going to divide these two to come up with my takeoff center of gravity. These numbers should be relatively close to each other. So 42.55 at the ramp weight, it's 42.53 for takeoff. So that's pretty good. Now, our total fuel burn, we said way down here was going to be 14 gallons, right? We rounded that up. So if we call it 14 gallons, we got to multiply that by 6 to come up with a weight. So if I take the 14 and multiply that by 6, got to move this little guy out of the way here. Multiply that by 6, that's going to give me 800, I'm sorry, not 800, it's going to give me 84 pounds. So I'm going to burn 84 pounds of fuel on this flight. This 84 pounds includes that 8 pounds of taxi fuel. So the way I've done it here was kind of also another mistake. But if you do it this way, you're doing another overestimate of your fuel burn. So you probably could have, instead of calling it 84, called it 78. Take that as you will. Ask your CFI about it if you're curious, or if you want different guidance. But in my opinion, this isn't really a terrible mistake in overestimating your fuel burn. But anyway, if I subtract my weight for my fuel burn, and then I subtract my moment for the fuel burn during the flight, I'll come up with that total moment. And then I can divide the two to come up with my landing center of gravity. And there you go. Make sure that you check that your weight and CG are within limits for each of these boxes. And then the day of your flight, make sure that you use your actual aircraft's empty numbers here. So the ones I'm marking in red are the ones you have to redo on the day of your flight. What this does right now is it gives you an estimate of what your weight and balance will be. Next up, now that we know our weight and balance, we can calculate our takeoff and landing performance. The reason why we need to know that is because your weight will affect how your aircraft performs during takeoff and landing. So we're going to start with our departure airport of KDBQ. We're going to figure out the temperature. We already know that was 5 degrees. We need to calculate our pressure altitude. So hopefully you remember this from ground school, or maybe you haven't learned it yet, but double check with your instructor, either ground or flight instructor if you're not sure. But remember that your altimeter setting at Dubuque was 3006. This is the same weather that I've been using for the whole video. And we're going to take a standard altimeter setting of 29902, and we're going to subtract what we have for our altimeter setting. So when we take 2992 and subtract the 3006, we're going to come up with a negative number, and that's totally fine, not a big deal. When we subtract these two, we get a negative 0.14, and you take that and multiply it by 1,000 to turn it into feet. So when you take it by 1,000, you come up with negative 140 feet. And then you add to this your field elevation. So negative 140 plus 1,077 means that my pressure altitude at Dubuque on the day of this flight is going to be 937 feet. So we could go back and interpolate performance data to 930 feet, or you can just make it easy on yourself and round your numbers up. So if we look at our short field takeoff we have 3 different charts. We have one for 2,550 pounds. We have one, and that's is shown up at the top there. We have one chart for 2,400 pounds and one chart for 2,200 pounds. Now we said our pressure altitude was 937, so if you want, again, you can just round this up to 1,000 feet. The numbers at 1,000 feet will be worse, I guess is the only word I can come up with right now, than what we're actually going to be able to perform at. So if you look here, 860 to 940, well, we're just going to take the 940 because if we can do it if we can take off in less than 940 feet, then 940 feet should be fine. So our pressure altitude, we're just going to call it 1,000. We know it's actually less than that. Let's go take a look at our ground roll. So again, our ground roll is going to involve some interpolation. We have a temperature of 5 degrees. Now 5 degrees is exactly halfway between 0 and 10. But first we have to make sure that we're on the right chart. So we have this chart that's at 25.5. This one here is the 2400 chart. And then remember the 2200 chart. So for our estimated weight and balance, we were close to 2,400 pounds. So that's the most appropriate chart to use. So when we go back that way, we're going to flip back to the 2400 chart here. Right there, I'm showing you here that we have the gross weight for takeoff is 8 pounds off of 2,400. So that's the most appropriate chart to use. And that's the whole reason why we needed to do this weight and balance. So when we flip back to our takeoff performance, we're going to use not the 2200, we're going to use this here 2400. We set our pressure altitudes at 1,000 and our temperature is at 5. So if you wanted to interpolate, you would have to interpolate between the 810 and the 875. You'll notice that the hotter the temperature gets, the worse your airplane performs. So you could interpolate halfway, or if you want to be safe and overestimate or give yourself a nice little buffer, under these particular conditions and liftoff speeds, I think I'm just going to end up taking the 875. Always be sure to check the notes section because there are a tailwind or a headwind will change these numbers. That's one thing that a lot of students mess up on. And so considering all of that, we need to figure out if we have a headwind, a tailwind, and what our crosswind component is as well. So here I'm showing that we're just going to use the temperature of 10 degrees because we don't feel like interpolating. We'd rather just be able to plan for a longer takeoff or worse performance. And we have to go figure out what is our headwind and what is our crosswind because they will affect these numbers. Now we're going to use takeoff. We're taking off at Dubuque where the winds are 030 at 8. That means our takeoff runway is probably going to be runway 36. So that would be a 30-degree difference in direction. So if we go to our crosswind table, our wind components table, we'll use the 30-degree line because 030 is 30 degrees off of runway 36. And we're going to figure out where about 8 knots is. So if we go to the left, that gives us a headwind. We go straight down, that gives us a crosswind. We see that our headwind is about 7 knots or so. That is not quite the 9 knots that we need to make the adjustments as the notes tell us to do on our takeoff performance. But we're just going to put our headwind here and our crosswind here so that we are familiar with what those are. So now that I know my headwind, I can go back to my 2,400 pound table at 1,000 feet pressure altitude. I'm just going to take the 10 degrees number, and that gives me a ground roll of 875 feet. And then to clear a 50-foot obstacle, I'm going to need almost 1,500 feet, so 1,495. So my ground roll is 875. The total takeoff distance to clear a 50-foot obstacle is 1,495. Now your accelerate stop distance is another point of confusion. Your accelerate distance is 875, but your stop distance is not the 1495. The stop distance comes from your landing table. So if you had to land at Dubuque at 1,000 feet pressure altitude with 10 degrees Celsius, I'm showing you here that there are no other, this is just maximum landing weight, 50 pounds. So a lighter weight, which we have, will give you shorter distances on your landing. We're going to take the 585 number. 1,000 feet, 10 degrees Celsius, 585 is the distance to stop your aircraft. So if we add those two together, we come up with our accelerate stop distance. And I always like to show it this way so that any instructor or anybody that wants to check it knows how I came up with 1460. My rotate speed for takeoff, we already kind of circled that previously, but we'll go back and show it here. Rotate speed is 48 knots, and the speed as I'm crossing a 50-foot obstacle should be 54 knots. And now we have calculated our takeoff performance. We're going to go do the same exact thing. We're going to do it based on our landing information. It'll start out much the same way. We're going to, in just a second here, we'll switch over to our destination airport, and we're going to fill in the information that we see there. So the first thing is going to be KRST, that's the Rochester Airport, and we'll record the temperature as well. Our pressure altitude is going to be calculated the same way. You'll have to pull the current METAR from Rochester. I didn't pull that for this video, but we're just going to assume that the pressure altitude is similar. So here I'm showing that, you would have your TAF for Rochester, and then you would have the current METAR for Rochester. But I don't have that here, so like I said, we're just going to assume that it is 1317, I think, is what we're going to use. Alright, so assuming then that we looked up the current METAR, let's just pretend like it says 1317. You can see I wrote down for temperature that we are going to use the 10 degrees Celsius. And for pressure altitude, let's just round that all the way up to 2,000. It's a pretty big a pretty big round up from 1,300 feet to 2,000 feet. But again, it's better to use worse performance calculations. That way you know that your airplane will actually be performing better. So for your headwind and your crosswind, remember, here I'm saying let's just use the 080 at 07. That's the winds from your TAF. So what the winds are expected to be. And with winds of 080, options for landing here, we see that we have either runway 13 at Rochester, or we have runway 2 at Rochester. So a 080 winds are coming from the east. And that's how I know we can use either runway 13 or 2. And what's going to be the determining factor is which runway has the least amount of crosswind. In other words, is closestly aligned with the runway. So here, to go from runway 02, otherwise runway 13, those are our options. And for runway 2, that's a 60-degree offset from the winds, and runway 13 is a 50-degree offset. So we'll just calculate as if we were going to land on runway 13. Now, when you actually get to Rochester, they might assign you a runway 2 just because it's only 10 degrees off from your other option, but not a big deal. We're going to go to our crosswind calculation, our wind crosswind component chart. So when we look at a 50-degree offset at 7 knots, we would show somewhere right in here, I just put a dot there, and that is a headwind of 5 knots and a crosswind of about 6. So we'll put that on our landing information. Pretty straightforward. Now again, the same note exists on our landing chart. It says that if you have a headwind or a tailwind, that you'll have to adjust your landing distance information. So over here on our landing chart, we're just going to say that we're at 2,000 feet and 10 degrees. So our ground roll is 610 feet, and our distance needed to clear a 50-foot obstacle is 1385. We're not going to adjust these numbers because the 5-knot headwind isn't really enough. Again, you could interpolate that if you want to be super precise, but we're taking the bigger numbers anyway, so no need to interpolate. Our speed, as we are 50 feet above the runway, should be 61 knots, so that's what we're going to say our approach speed is. And now you have calculated your takeoff and landing information. Next up is your cruise information. This is pretty straightforward. We already know all of this. So for cruise performance, we said our pressure altitude is 4,500, so we'll fill that in. Our outside air temperature, that we know came from our calculated at altitude temperature of -2 degrees. And then this information here, we already said we're assuming 70% horsepower, RPM of 2,500. We don't have manifold pressure in our Cessna, and our fuel burn rate was 9.7 gallons per hour. We just round that up to 10 because we're going to overestimate our fuel burn. Next, you got to fill in all that chart supplement information. So a lot of that is frequencies. Hopefully you're familiar with how to look up frequencies. Make sure you fill all that in. I'm not going to spend time on this video looking up information, but I do want to point out there that you got to fill it all in. So traffic pattern altitude and then elevation. So for your departure airport is the top box, and the bottom box is for your arrival airport. Just draw your runways in there. Pretty straightforward, pretty easy. You know, here I'm showing you, here's Dubuque, and here's Rochester. I wrote the numbers upside down. That part's pretty straightforward as well. Don't forget your traffic pattern altitude is probably the one that a lot of students get confused on. So that part's pretty easy as well. Fuel blocks. How to fill in the information about your fuel burn. So that's up on the front page. We have time, gallons per hour, and total gallons and pounds for taxi, takeoff, cruise, approach, and then what the reserve is that we require at UD. So the time that we taxi is pretty variable. Let's just say that it's 12 minutes. Your gallons per hour during taxi, we don't really know that. You know, if you wanted to look at it in the airplane, you could. But we know that the POH says to plan on 1.4 gallons for your startup and run up and taxi. So that's 8.4 pounds. Now during your takeoff climb, we said that we had a total of 6 minutes for our climb. And again, there's really no gallons per hour for this bit, but we know that we're going to end up with 1.3 gallons that we burn. That came from our time distance fuel to climb table. And I keep zooming out because I'm looking in the bottom left to show you, to see how much I have already calculated for these things. So remember, in the traffic pattern, we say that our approach is going to be 6 minutes. we said that in cruise we were going to burn 10 gallons per hour, and we have a total of 71 minutes for everything. So if I take off my climb and I take off my approach, 71 minutes minus 12 minutes is the amount of time that I will be in cruise. So on my calculator, it shows up to be 59 minutes, which means I should burn just about 10 gallons for this flight. And so that'll be 60 pounds. The approach, well, gallons per hour, I call it 10. We know it's going to be less than 10, but if we calculate it as 10, again, we're overestimating, and so that's a better way to make an error rather than underestimating. So that'll be 0.1 gallons at 0.6 pounds, and then we're going to assume that UD requires us to have 1 hour of fuel reserve. That's not an assumption, that's actually what it is. So again, if we call it 10 gallons per hour, there you go, you need another 10 gallons. And then I forgot my pounds for takeoff climb there. Don't forget to fill that in. And so I said 1 hour, it's 60 minutes. That's my fault. Then we just total all this stuff up. So total fuel required is what we really want to make sure you understand is needed for your flight. If the number you come up with is more than 53 gallons, you need to redo your planning or change something, because you can only hold 53 gallons in your Cessna. I put a line in the box there for gallons per hour, just because it varies throughout your entire flight. But the total gallons needed is 22.3, which is 136.8 pounds. Alright, so this thing is starting to look pretty well completed. We still have a couple other things that we have to do though, and one of those is making sure you understand where you got your weather briefing from. So you can get a weather briefing in ForeFlight. If you don't know how to do that, we'll make a video and show you, so you can go check that one out. 1-800-WX-BRIEF you can call, or you can go to 1-800-WXBrief.com. And whichever method you use, be sure that you email your briefing to udflight@dbq.edu. A lot of students don't even know that. So make sure you do that. It is required. We want to have a copy of the briefing that you got in the event that something happens and we need to know what your planning was like. Alright, don't forget about your risk assessment and the flight plan section itself. So the risk assessment is pretty straightforward. I think you can read through all that. And your day of departure checklist, don't forget to go through that as well on the day of your flight. Pretty straightforward things. Just give yourself a score, mitigate risk if you can, and however you can. Don't forget to fill out the pilot and passengers information. And then while you're in flight, you'll have to do your en route procedures checklist. So that's something that is pretty straightforward. It's just you filling in all of the actual times. But what we're looking at here is the type of flight plan, or I'm sorry, the actual flight plan that we're going to fill out. So we're assuming this is a VFR flight. And one of the biggest things that gets forgotten on these flight plans is your N number, because that's something that you do the day of when you know what actual airplane you got. So don't forget to go back and fill that in. Your type of airplane is a C-172. It is not a 172S. It's not a C-172S. It's just C-172. Your weight category is light. Your aircraft weighs less than 12,500 pounds. And so L is what we put in that box. We have an entire video dedicated to these equipment codes and why they are the way that they are. But for now, in this video, just know that your radio and nav equipment is S, B, G, and R. Your surveillance equipment is E and B2. Departure, we already know that's KDBQ. The departure time is in Zulu time. So it's a 4-digit code. So whatever time in Zulu. Your true airspeed, we already know that was 113. Your level, your altitude should be A045. That means altitude, and then you add 2 zeros onto the end. So 045 means 4,500 feet. Our route is direct, so we put DCT. And our destination is KRST. The time en route is in the hours, minutes format. So we're going to say that this is, 71 minutes. So 1 hour, so 01, and then 11 is the number of minutes. So an hour and 11 minutes. Our alternate, for a VFR day flight, we're not required to file one. But if you want to know more about how to determine an alternate airport, it needs to be somewhere that you can go in the event that you're not able to land at your intended destination. So we don't want somewhere that's too close, because if we're having to divert for weather, if we pick something that's really close, then the weather might be the same as it is at our intended destination. So here I'm just kind of showing that there's a bunch of different options that we have for where we can go. We could go to this airport here. That one there's pretty close. If we wanted to go really far south, Mason City or even Waterloo, holy cow, that's almost all the way back to where we departed from. Maybe we would continue all the way out to Mankato. La Crosse might be an option. And so for this, I'll just arbitrarily pick one. Let's say that we're going to call Mason City our alternate. So KMCW. Next up, remarks for PBN. We need to put C2 and D2 in there. Again, there's a whole video on these equipment codes, but for now, just know that that's where you got to go. All right, how much fuel do we have on board? Well, we said that we were going at about 70% power at 4,500. So we're going to come to our endurance chart, and we're going to look at 4,500, and about halfway between the 75 and the 65 is where we're going to find our 70% power. And if we go straight down on that, it shows a little bit more than 4.5. That bar right there is 4.5 hours. So we might end up with like 4 hours and 40 minutes or something like that. But if we're going to estimate and we're going to make an error, let's call it shorter than we actually will have. So we're just going to say that we have 4 hours and 30 minutes of fuel on board. So again, hours, minutes. So 0430. Me and my flight instructor are on board. Don't forget to put in your information here. You are the pilot. Colors for our Cessnas, we just put white. Destination contact, UD wants to know this. This is not actually this part here won't get filed with the FAA. And then who do you need to close with? The flight service station that you're going to close with up at Rochester. Well, let's go to our map and see which flight service station is up at Rochester. Here, this is Mason City, so it would be Fort Dodge, 122.6. Rochester is probably Fort Dodge as well, but let's just pretend for this video that we actually looked at Rochester's information. Alrighty, things are coming together nicely. One of the last things you have to do on your flight plan is make sure that you sign it, you complete it, and that whoever reviews it signs it as well. And one last note, Rochester actually has a flight service station of Princeton, so just keep that in mind. It's not always going to be Fort Dodge. Thanks for watching.